All right, get ready to unlock some cool secrets about square numbers and their roots. We're diving deep into these unique numbers, pulling from excerpts of an actual math textbook. But don't worry, no pop quizzes here. By the end of this, you'll be spotting square numbers left and right, understanding their patterns, and maybe even surprising your friends with some slick math tricks.
What's fascinating is how often we encounter square numbers without even realizing it. You ready to start unraveling these mathematical mysteries?
Absolutely, I'm all in. Our source material starts with the concept of area, particularly of a square. Now, we all know a square has four equal sides, right? But what's interesting is how the area ties into this whole square number thing. What's the connection?
So imagine a square with sides of length a. The source points out that to find the area, you multiply the length of one side by itself, a times a. And guess what? That gives you a squared. That's where the term square number comes from. It's literally representing that area.
Okay, I'm seeing the visual here. So when we talk about perfect squares, we're talking about numbers you get from squaring a whole number. Like 16 is a perfect square because it's 4 times 4.
Exactly. And the source emphasizes this with a challenge. Try these questions. One asks us to find the perfect squares between 30 and 40. Can you spot it?
Let's see. 5 squared is 25. 6 squared is 36. That fits.
Nicely done. See how quickly you're already recognizing those perfect squares.
It's like a superpower. But I'm curious. The source also makes a point of saying that not all numbers are square numbers. They use the example of 32. What's going on there?
Well, think about the numbers you could multiply by themselves to get 32. There's no whole number between 5 and 6 that would work. This distinction is important sometimes. Understanding what something IS means, also understanding what it isn't T.
That's a really good point. So before we dive into all the cool patterns hidden within square numbers, why does any of this even matter?
Well, let's bring it back to that area example. Whether you're planning a garden, rearranging your furniture, or even just trying to figure out if that new rug will fit. Understanding area is essential.
It's like math is secretly running our lives.
Yeah.
Okay. Ready to decode some more secrets about these numerical marvels?
Absolutely. Let's unravel some of these fascinating patterns.
All right, hit me with your best shot. What cool patterns are hidden within square numbers?
Prepare to be amazed. Because square numbers have some pretty unique characteristics. For example, have you ever noticed that a square number can never end in a 2, 3, 7, or 8?
Wait, really? I'm going to need an example here. My brain needs convincing.
Of course. The source uses the number 1057. It ends in a 7, which automatically tells us it can't be a perfect square.
Okay, I see it. But why is that? Is there some mathematical reason behind it?
There absolutely is.
Yeah.
It all comes down to something called cyclical patterns in mathematics. To see it in action, start squaring numbers from 0 to 9 and take note of the last digit of each result.
Okay, so 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So last digit 6, 5 squared is 25, last digit 5.
You're getting it. And if you keep going, you'll notice those last digits, we call them units digits, they repeat in a specific order. 0, 1, 4, 9, 6, 5, 6, 9, 4, 1. And guess what's missing from that cycle?
The 2, 3, 7, and 8. No way! That's crazy. So just by looking at the last digit of a number, I can rule out whether it's a square number or not.
Exactly. You're already starting to think like a mathematician, spotting those patterns.
Love it. It's like cracking a code. Speaking of patterns, what about those trailing zeros in some square numbers? Like what happens when you square a number ending in 0?
Well, let's take the example of 100, which the source uses. 100 squared is 10,000. Notice anything interesting about the zeros?
Hold on. There were 2 zeros in 100, and now there are 4 zeros in 10,000. Did they double?
They did. That's the pattern. Square a number ending in 10, you get 2 zeros in the result. 2 zeros become 4, and so on. It's a neat little shortcut for those larger squares.
Okay, that is seriously helpful. I'm already starting to see how understanding these patterns makes squaring numbers so much easier, even without pulling out a calculator.
Exactly. And it gets even cooler. Remember those triangular stacks you mentioned earlier, like bowling pins? The source calls those triangular numbers. And guess what? They're connected to square numbers too.
Wait, seriously? Those visual patterns are related to squares? How does that even work?
Think about building a square, layer by layer, using dots. The first layer is just 1 dot. The next layer needs 3 dots to make a bigger square, then 5 more dots, and so on. You're adding consecutive odd numbers each time.
Okay, I'm picturing it. So how does that relate to triangular numbers?
Each of those layers, 1 dot, then 3, then 5, forms a triangular number. Add 2 consecutive triangular numbers, and you get a perfect square.
Whoa, you're blowing my mind here. Do you have an example? This is wild.
Take the 4th triangular number, which is 10, 1 plus 2, 3, 3, 4. The fifth is 15. Just add 5 to the previous one. Add 10 and 15, and you get 25, which is 5 squared.
No way! It's like a hidden code within the numbers.
Yeah.
All right, I'm convinced square numbers are way more interesting than I thought. What other patterns are lurking out there?
Well, the source also points out a pattern with the numbers between perfect squares, like between 9, which is 3 squared, and 16, which is 4 squared.
You mean how many numbers are in between? Let me see. There are 6 numbers between 9 and 16.
Exactly. And if you look at 16, which is 4 squared, and 25, which is 5 squared, there are 8 numbers in between. The source calls this the 2-end pattern.
Okay, break that down for me. What does 2-end even mean in this context?
Think of n as the smaller of the two numbers you're squaring. So between 3 squared and 4 squared, n would be 3. Multiply that by 2 and you get 6, the number of digits between the squares.
No way it works. It's like a magic trick. Math is so much cooler when you see the tricks behind it.
It certainly is. And speaking of tricks, the source offers a really neat way to find squares without having to do the full multiplication out each time.
Okay, you have my full attention. My mental math skills need all the help they can get. What's the secret?
It's about breaking down the problem into smaller, more manageable chunks. Let's take 23 squared as an example. Instead of multiplying 23 by 23, the source suggests thinking of it as 23 squared.
I see. But why is that helpful? It seems like we're adding more steps, not simplifying things.
Here's where it gets clever. Remember how to square a binomial. You end up with 20 squared plus 20 times 3, twice, plus 3 squared. Now you're dealing with smaller squares and multiplications, which are much easier to handle mentally.
I'm actually following this. And yeah, I could definitely square 20 and 3 in my head way faster than figuring out 23 times 23. That's a game changer.
Right. And this approach isn't just for mental math. It's a powerful problem-solving strategy in general. Break down complex problems into smaller solvable parts, and suddenly it all becomes manageable.
I'm starting to see the bigger picture here. It's not just about the numbers themselves. It's about the way we think about them.
Exactly. And speaking of thinking about numbers in different ways, have you ever heard of Pythagorean triplets?
Pythagorean triplets, those ring a bell, but I need a refresher. What are they again?
They're like a mathematical dream team. Sets of 3 whole numbers, where the sum of the squares of the first 2 equals the square of the third. The most famous example straight from our source is 3, 4, and 5.
Right. 3 squared plus 4 squared equals 5 squared. It's like a mathematical equation that just feels right. But is there more to them than just this elegant relationship? What makes them so special?
Well, for one, they pop up in geometry all the time, especially when dealing with right triangles. Remember the Pythagorean theorem? Pythagorean triplets are basically ready-made solutions to that equation.
That makes sense. So we can use them to quickly figure out side lengths of right triangles. That's super handy. But before we get too caught up in triangles, we've been talking a lot about squaring numbers. What about going in reverse, finding square roots?
That's where things get really interesting. The source draws a great analogy. Just like addition and subtraction are inverse operations, so are squaring and finding square roots.
So if 4 squared is 16, the square root of 16 would be 4. It's like hitting the undo button.
Exactly. And the source walks through a few methods for finding square roots. They mention repeated subtraction. Basically, you keep subtracting consecutive odd numbers from the number you're working with until you hit 0. The number of subtractions is your square root.
That seems straightforward enough for smaller numbers. But I can imagine it getting a bit tedious if you're dealing with, say, 1024.
You're right, which is why, for larger numbers, the source introduces us to the power of prime factorization.
Okay, prime factorization. It feels like every time we dive into a new area of math, prime numbers make a grand entrance. What makes them so special in this context?
Well, let's use the source's example. Finding the square root of 324. First, you break it down into its prime factors. 2 by 2 by 3 by 3 by 3 by 3 by 3. Then you pair up those factors, 2 by 3 by 3. Multiply those paired factors, and you get 18, the square root of 324.
It's like prime numbers are the building blocks of all numbers. And prime factorization helps us see how those blocks fit together to form squares. That's incredibly insightful.
It is. And while prime factorization is a powerful tool, the source also mentions a more practical method for larger numbers, the long division method for square roots.
Long division for square roots? That sounds a little intimidating, to be honest. Is it as complicated as it sounds?
It's not as scary as it might seem at first. It's just a series of steps you follow, and it can be surprisingly satisfying once you get the hang of it. Want to try an example together? Let's find the square root of, say, 529.
Okay, I'm game. Let's see if I can keep up with this mathematical magic trick. Walk me through it.
All right, so first we group the digits of 529 into pairs, starting from the right. That gives us 529. Now think about the largest perfect square that's less than or equal to 5.
That would be 4, which is 2 squared.
Perfect. That 2 becomes the first digit of our answer, and we'll use the 4 as our first divisor. Now subtract 4 from 5, leaving us with 1, and bring down the next pair of digits, 29. So now we have 129.
Okay, I'm following so far. We've used the 2 and have 129 left to deal with. Now what?
Now we double that first digit of our answer, the 2, which gives us 4. Write it down with a little space to its right, like this. 4. We need to find a digit to fill in that blank so that when we multiply 4 by that same digit, the product is less than or equal to 129.
Let's see, if we try 3, then 43 times 3 is 129. That works.
Exactly. That means the square root of 529 is 23. We've done it.
Wow! I can't believe it. I actually followed along and found a square root using long division. That's another mathematical superpower unlocked.
You're getting it. And the best part is this method works for even larger numbers. It just might require a few more snacks to power through all the steps.
I'm all about that snack-powered math. This has been incredible. We've gone from basic definitions to uncovering hidden patterns and even mastering methods for finding square roots, all in one deep dive.
And we've only just scratched the surface. There's a whole universe of mathematical wonders waiting to be explored.
Absolutely. So for our listeners, I have a challenge for you. Think about your day-to-day life. Where do you see square numbers popping up? Can you apply any of the techniques we've talked about? I bet you'll start to see the world in a whole new way, noticing the elegance of square numbers hidden in plain sight.
Until next time, keep those minds curious and stay excited about the power of numbers.